Hello, Mr. Sutton here with the AB Calculus 3.8 Extra Practice Number 4 solutions on implicit differentiation. On this problem, we're trying to find the derivative of y with respect to x, but since y is difficult to isolate, we're going to use implicit differentiation. So going from left to right, we've got 3x squared plus 3, and then the derivative of y squared, that's going to be 2y times dy over dx, since y is considered an inner function here. And then this is going to equal 2 dy over dx, and then that 1 is just a 0 if you differentiate that. All right, let's get the dy over dx's on one side and everything else on the other side. So let's see here. This 2 dy over dx, that can stay on the left side, and we're going to subtract this 2 dy over dx to be over with the 2y dy over dx. And then we'll move these other two terms that don't have dy over dx's over to the other side. So we can say equals negative 3x squared minus 3. Next, let's factor out that dy over dx. That leaves us with 2y minus 2 inside. And then I'll just divide both sides by that parentheses. So we have negative 3x squared minus 3 over 2y minus 2 equals dy over dx. On this problem, to find dy over dx, since y is going to be kind of a pain to isolate, and we're going to have to deal with a plus or minus, we're just going to use implicit differentiation here. So going from left to right, 4x squared's derivative, that's going to be 8x. And then the derivative of 9y squared is going to be 18y times dy over dx, since y is considered an inner function of x. And then 36, that's just going to be 0 if you take that derivative. Okay, so let's just move this 8x over to the other side. And we're just isolating dy over dx now, so we can divide both sides by 18y. And that's going to give me, let's see here, negative 4 over 9 if I reduce that. So negative 4x over 9y is my final answer for dy over dx. For this problem, since y is going to be kind of annoying to isolate, implicitly differentiating is the best way to get dy over dx. So let's start by taking the derivative of everything from left to right, and we'll treat y as an inner function of x. To do this x times sine of x deal, we need to do the product rule. So let me set up my box and ribbon here, and I've got factors of x and sine of x, whose derivatives are 1 and cosine of x. Using the ribbon to multiply that out, we've got 1 sine of x, so just sine of x then, plus x cosine of x. And now we move on to the cosine of y. Derivative of that is going to be negative sine of y times dy over dx, because again, y is its own function of x. So we have to use the chain rule. And then that's going to equal derivative of 3x minus 1, which is 3. All right, now we're going to isolate this term that has the dy over dx. So all we have to do is subtract the sine of x and the x cosine of x to the other side. So we'll have 3 minus those two terms. And then we just divide everything by negative sine of y to get dy over dx by itself. So we end up with all the stuff that's already on the right side divided by negative sine of y. On this problem, we're trying to get dy over dx, which is kind of problematic because y is very difficult to isolate here. So we're just going to go straight to implicit differentiation and see what happens. Differentiating everything now from left to right. Let's start on the left side here. Derivative of tangent. This is a chain rule we're going to have to use. So we've got tan of something. The derivative of that is going to be secant squared of something. So secant squared of x squared times the derivative of x squared. So that's times 2x. And then on the right side, we've got a big chain rule going on here as well. The outer function is something cubed. This whole cosine of all this stuff is being cubed. So the derivative of something cubed is going to be 3 times something squared. So in this case, cosine squared, or actually 3 cosine squared of y squared plus 2. And then we're going to multiply that by the next function in, which is the cosine function. So the next function, we've got cosine of something. The derivative of that is going to be negative sine of something, so negative sine of y squared plus 2. And then finally, we have the y squared plus 2 inner function to deal with. Derivative of that is going to be 2y, but y itself is an inner function, so we have to multiply by a dy over dx. All right, so that was pretty crazy. The good news is that to get dy over dx by itself, we actually only have one step. all of this stuff on the right side of the equation is being multiplied by dy over dx. So to get dy over dx by itself, we just have to divide by everything that's not dy over dx on the right side of the equation. So we're going to end up with secant squared of x squared times 2x divided by all of this stuff. 3 cosine squared, negative sign of that stuff, 2y, all of it moving down to the denominator here. For this problem, I'm trying to find the derivative of y with respect to x. That's a little tricky here because to isolate y, I'm going to have to do inverse tan, and maybe you don't know the derivative of inverse tan at this point in your calculus studies. So we're going to use implicit differentiation instead. That doesn't require us to know tan inverse derivatives. So going from left to right, just taking the derivative of everything with respect to x, we've got 3 cotan of x. That's going to become negative 3 cosecant squared of x. And on the right side, 2 tan of y, that's going to become 2 secant squared of y times the derivative of y, because y is itself a function of x. So that's going to be a dy over dx tail that we need to throw in there. And then to get dy over dx by itself, just divide both sides by 2 secant squared of y. So we end up with dy over dx equals negative 3 cosecant squared of y over 2 secant squared of y. And I'm sure you could simplify that to some other trig function, but we don't need to. We're just going to call it a day on this one. For this problem, I'm trying to find dy over dx. Since y is kind of a pain to isolate, I mean it's doable, but you know there's faster ways. Let's just imp diff this thing. So we're taking the derivative with respect to y, or respect to x rather, from left to right. On the left side here, x squared times y, that's going to require the product rule. So I have factors of x squared and y, whose derivatives are 2x, and the derivative of y is going to be dy over dx. Remember, y is itself a function of x, treated with the chain rule there. So now using the ribbon to multiply this out, we've got 2xy plus x squared dy over dx. And now we move on to the next term here, 3x, that's going to be a 3. And that's going to equal the derivative of y, which we just said is dy over dx. All right, next we're going to get all the dy over dx's on one side so we can factor out a dy over dx. So let's get them all on the left here. X squared dy over dx can stay over there. I'm going to subtract this dy over dx to be over there. And all the other stuff's got to move to the right side. So negative 2xy minus 3. And now on the left side, I can factor out a dy over dx. That leaves me with x squared minus 1, which I can then divide both sides by. So dy over dx is going to be negative 2xy minus 3 over x squared minus 1. For this problem, we don't actually have to do a whole lot of heavy algebra. They're just asking which of these following problems here would require the use of implicit differentiation to find the derivative. So imp diff, you're going to need to use that whenever you can't isolate y. If you can isolate y, then you don't have to use imp diff. It still might be more convenient, but you don't have to. For example, choice A, you might think, okay, this is an imp diff situation. Y is not by itself on one side of the equal sign, but you could add all this stuff to the other side and get y by itself and then take the derivative. So you don't need imp diff for choice A. Same thing with choice B. You could already take the derivative here. Choice C is a different story. So in choice C, y is not isolated, and it's pretty much impossible to isolate y in this situation. To get y out of this ln, you're going to have to raise e to both sides. But then this y over here is going to be stuck inside an e. And then to get it out of the e, you're going to have to take the ln again, and it's just a mess. And then choice D, we already have y isolated, so that's not an issue. So choice C then is the only one we can't isolate y in. So that means choice C is the only one that requires imp diff.